Hello everyone, this is Amit Brambhat. I'm a professor for CSC 208 at Laurel Ridge Community College, and today we are going to talk about logic and proof and related topics. Let me go ahead and share my screen with you. So we'll be trying to understand logic and proofs in discrete mathematics. We'll try to understand propositions and truth values, logical operators, compound statements, truth tables as tool for logical analysis, etc. So first we need to understand importance of logic and then role of proofs and how logic is used in technology. If you've taken CSC 110, you might remember and, or, and not gates and the exercise we had around it. Logic is the backbone of discrete mathematics and a critical skill for students in computer science, cybersecurity, data science, and information systems. At the community college level, for this course's context, logic provides a formal way to describe correct reasoning, allowing us to distinguish valid arguments from invalid ones using precise rules rather than intuition. Discrete mathematics relies heavily on logical structure because it focuses on objects such as integers, graphs, sets, and algorithms, all of which require exact definitions and unambiguous reasoning. One key purpose of studying logic is to build the ability to read and write mathematical arguments, commonly called proofs, with clarity and confidence. Proofs are not just academic exercises, they are also used to verify that algorithms work correctly, that programs behave as intended, and that the systems are secure against errors or attacks. For example, when a software engineer proved that a sorting algorithm always produces correctly ordered lists, they are using logical reasoning, similar to what is learned in this chapter. Another important motivation for studying logic is its role in everyday technology. Search engines, database queries, and digital circuits all rely on logical operators such as and, or, not, etc. Even simple decision programs like whether a user can log in or whether a loop should be continuing to run are based on logical expressions. By learning formal logic early in discrete mathematics, students develop a foundation that supports later topics such as set theory, functions, and proofs by induction and graph theory. This slide introduces the big picture. Logic is the language of reasoning in mathematics and computer science, and mastering it will make later topics more understandable and less intimidating. Understanding propositions and truth values. A proposition is one of the most basic building blocks of logic. Formally, proposition is declarative statement that is either true or false, but not both. This clear definition is important because logic depends on ability to assign truth values consistently. Examples of propositions include statements like 2 plus 2 is 4, which is true, and 7 is an even number, which is false. In contrast, questions, commands, or vague expressions are not propositions. For instance, what time is it or close the door cannot be assigned a truth value and therefore do not qualify. Similarly, statements like this sentence is interesting are too subjective to be treated as propositions in formal logic. In discrete mathematics, propositions are often represented by lowercase letters such as P, Q, and R. This abstraction allows us to focus on the structure of logical arguments without getting distracted by specific wording. Truth values, typically denoted as T, true, and F, false, are assigned to these propositions and used to evaluate more complex logical expressions. Understanding propositions is essential because they form the inputs to logical operators and truth tables, which are used extensively later in the course. For example, in computer programs, conditions inside an if statement are propositions that evaluate to true or false at runtime. In mathematics, propositions appear in theorems and definitions, where determining their truth is the goal of a proof. By learning to clearly identify propositions and their truth values, students gain the ability to translate real-world statements into precise logical form, a skill that is crucial for problem solving in both academic and professional settings. So what are the logical operators and compound statements? We have negation operator, we have conjunction operator, disjunction operator, and implication operator. Logical operators are used to combine simple propositions into more complex statements called compound propositions. The most common logical operators in discrete mathematics are negation or not, conjunction or and, disjunction or, and implication if then. Negation, written as not P, reverses the truth value of proposition. If P is true, not P is false, and vice versa. Conjunction, written as P and Q, is true only when both P and Q are true, which mirrors how the word and is commonly used in everyday language. Disjunction, written as P or Q, is true when at least one of P or Q is true, including the case where both are true. This inclusive meaning of or is important, especially in programming and logic circuits. Implication, written as P implies Q, represents if P, then Q. Relationship often causes confusion at first. In logic, P implies Q is considered false only when P is true and Q is false. In all other cases, it's true. Understanding why this definition is useful becomes clearer when studying proofs and program correctness. Compound statements allow us to model complex conditions, such as a student passes the course if they complete the assignment and pass the final exam. Logical operators are fundamental in designing algorithms, writing conditional statements and in code, and analyzing logical arguments. Mastery of these operators enables students to move fluently between English descriptions and symbolic logic, which is a key goal of discrete mathematics. Truth table as a tool for logical analysis. Truth tables are a systematic method for analyzing logical expressions by listing all possible combinations of truth values for their component propositions. For each combination, the truth value of entire compound statement is calculated using the definition of the logical operators involved. This process removes ambiguity and provides a clear, mechanical way to evaluate logical expressions. For example, truth table for implication P implies Q includes 4 rows representing all combinations of P and Q being true or false. By filling the table, students can see exactly when the implication is false and when it's true. Truth tables are especially useful for comparing logical expressions to determine whether they are logically equivalent, meaning they have the same truth value for every possible assignment of the truth values. In computer science, truth tables are closely related to digital logic and circuit design, where inputs and outputs are either on or off. They also play a role in verifying program logic, such as checking whether a complex condition behaves as intended in all cases. Although truth tables can become large when many variables are involved, they provide an important conceptual foundation. Later in the course, students may use algebraic techniques or logical laws to simplify expressions instead of writing full tables. But the underlying idea remains the same. Learning how to construct and interpret truth tables builds confidence and accuracy in logical reasoning, making them an essential tool in discrete mathematics. Logical equivalence and rewriting statements, predicates and the role of variables, quantifiers, universal and existential statements are the next set of ideas we are going to explore. Logical equivalence and rewriting statements. Logical equivalence refers to the situation where two different logical expressions always have the same truth value, regardless of the truth value of their individual variables. When the two statements are logically equivalent, they can be used interchangeably in proofs, programs, or logical arguments. One classic example is the equivalence between the implication P implies Q and the expression not P or Q. Although these statements look different, a truth table shows that they match in every possible case. Recognizing such equivalence allows students to simplify complex logical expressions and better understand their meaning. Logical equivalences are governed by a collection of laws, such as De Morgan's laws, which explain how negation interacts with conjunction and disjunction. For example, not in bracket P and Q is equivalent to not P or not Q. These laws are not arbitrary. They can be justified using truth tables and are widely used in mathematics and computer science. In programming, rewriting conditions using logical equivalence can make code clearer and more efficient. In database queries, equivalent logical conditions may lead to better performance. In proofs, replacing the statement with an equivalent one can make an argument easier to follow. By practicing logical equivalence, students develop flexibility in their thinking and learn that the same idea can be expressed in multiple correct forms, a skill that is valuable across many technical disciplines. Predicates and role of variables. While propositions have fixed truth values, predicates extend the idea of propositions by including variables. A predicate is a statement that becomes proposition once specific values are substituted for its variables. For example, the statement x is greater than 5 is not a proposition by itself because its truth depends on the value of x. However, once we assign x to 7, the statement becomes true, and if we assign x to 3, it becomes false. Predicates are essential for expressing general mathematical statements and rules. They allow us to describe properties of numbers, objects, or data in a precise and flexible way. In discrete mathematics, predicates are often written using notations such as P of x or Q of xy, emphasizing that their truth depends on one or more variables. Predicates are widely used in computer science, particularly in specifications and assertions about programs. For instance, a predicate might describe a condition that must always hold true before or after function runs. Understanding predicates helps students transition from simple logical statements to a more powerful expression involving entire sets of values. This concept prepares the way for quantifiers, which specify how broadly a predicate applies. Mastery of predicates strengthens students' ability to interpret definitions, write precise conditions, and understand formal mathematical language. Quantifiers, universal and existential statements. Quantifiers are symbols that indicate how many elements in a domain satisfy given predicate. The two most common quantifiers are the universal quantifiers written as for all, which looks like an inverted A, and the existential quantifier, which looks like a reverse of E, meaning there exists. A statement such as for all x in bracket x plus 1 greater than x asserts that predicate x plus 1 is greater than x is true for every possible value of x in the domain, such as the set of all real numbers. In contrast, the statement there exists x squared equals 4 claims that there is at least one value of x for which the predicate is true. Quantifiers are powerful because they allow mathematicians and computer scientists to express general rules and guarantees. However, they must be used carefully as changing the order of quantifiers can completely change the meaning of a statement. For example, for all x, there exists a y, where y is greater than x has a very different meaning from there exists y for all x, y is greater than x. In proofs, understanding quantifiers is essential for knowing what must be shown and what can be assumed. In programming and databases, quantifiers appear implicitly in loops and queries, such as checking whether all records meet condition or whether at least one record does. Learning to read, write, and negate quantified statements is a crucial step in becoming comfortable with formal reasoning in discrete mathematics. Proof techniques and applications. Proofs are structured arguments that demonstrate why a mathematical statement must be true. In discrete mathematics, several proof techniques are used repeatedly, each suited to different types of problems. A direct proof starts from known facts or assumptions and uses logical steps to reach the desired conclusion. Proof by contrapositive involves proving an implication by showing that if the conclusion is false, then the hypothesis must also be false. Proof by contradiction assumes that the statement to be proved is false and then derives a logical contradiction, showing that the assumption cannot be correct. Mathematical induction is used to prove statements about integers, especially those involving sequences or recursive definitions. Each technique relies on logical reasoning and a clear understanding of implications and quantifiers. Learning multiple proof strategies gives students flexibility and confidence when approaching new problems. Proofs are not just theoretical, they are used to verify algorithms, establish properties of data structures, and ensure correctness in computational systems. By practicing these techniques, students improve their problem-solving skills and learn to communicate complex ideas in clear, logical manner. Why logic and proof matter in computing? Well, logic and proof plays a central role in many areas of computing and information technology. In programming, logical expressions determine how programs make decisions, control loops, and respond to user input. In databases, logical conditions are used to filter and retrieve data accurately. In cybersecurity, logical reasoning is used to analyze protocols, verify authentication methods, and identify vulnerabilities. Proofs provide a way to guarantee that systems behave as intended, even in edge cases that are difficult to test experimentally. For example, proving that an algorithm always terminates or always produces the correct output can be more reliable than running it from on many sample inputs. Logic is also foundational in emerging fields such as artificial intelligence, where reasoning systems use formal logic draw conclusions from data and rules. For community college students like you guys preparing for technical careers or further study, understanding logic and proof builds a strong intellectual toolkit. It enhances critical thinking, attention to detail, and ability to justify conclusions, all of which are valuable skills in both academic and workplace settings. Finally, practice and applying logical reasoning. Developing skill in logic requires practical and active engagement with problems. Building truth tables, rewriting statements using logical equivalence, and working with quantified expressions all help reinforce key concepts. Simple exercises such as determining whether two expressions are equivalent or identifying the negation of quantified statement build confidence and accuracy. More advanced practice involves writing short proofs or explaining why a particular argument is valid or invalid. Applying logical reasoning to real-world scenarios, such as analyzing program conditions or interpreting system requirements, helps students see relevance of what they are learning. Group discussions and step-by-step explorations can also be valuable, as they expose students to different ways of thinking about the same problem. Over time, logical reasoning becomes more intuitive, but it's always grounded in precise definitions and rules. This final slide emphasizes that logic is a skill developed through consistent effort and reflection, and that mastery of logic and proofs will support success throughout the rest of the discrete mathematics course and beyond. I hope you enjoyed this presentation. I'll see you in the next class. Here now.